In this video, we're going to look at how to calculate the pH of solutions that result from hydrolysis reactions. In acid-base chemistry, hydrolysis has a very different definition than in organic chemistry, where in organic chemistry, hydrolysis refers to the adding of water in order to break a polymer into separate monomers. But in this case, the word hydrolysis is used more literally, where the suffix lysis basically means to break or to split, and hydro is of course referring to water. So in this case, the literal definition of hydrolysis is the breaking of water. Now, in acid-base chemistry, water can either be broken or changed rather to form either OH- if we're dealing with a basic compound, or H3O+ if we're dealing with an acidic compound. So when dealing with a salt here, the first thing to figure out is to whether this salt is going to behave as an acid or a base once it's dissolved. Well, we know that this compound is going to fully dissolve in water because, according to the solubility rules, all ammonium compounds are fully soluble in water, which means this is going to dissociate into the ammonium ion and the chloride ion. Now, in terms of predicting what's going to happen next, we remember that if we consider chloride to be a base, its conjugate acid is hydrochloric acid, but hydrochloric acid is a strong acid, meaning that it is going to ionize 100% of the way, meaning that chloride cannot undergo a reverse reaction in order to get HCl back. So because of this, chloride is treated as a spectator ion, meaning that once ammonium chloride dissolves, the chloride is just going to sit there and not undergo any reaction with water, and therefore does not need to be considered. Therefore, the molecule that undergoes hydrolysis, that means a reaction that involves the breaking of water in some way, is, of course, ammonium, which we know is going to behave as a weak acid when we put it into water. So water is going to pull the extra hydrogen off of ammonium in order to give us the conjugate base ammonia and H3O+, therefore functioning as an acid ionization reaction. Now, solving this particular calculation is a little bit different because we actually know what the pH value is, and therefore we can calculate the concentration of H3O+ by simply doing 10 to the negative pH as an exponent. And we actually need to work backward in order to figure out what the concentration of NH4+ is at the initial time. So here, we don't know what our initial concentration of NH4+ is. All that we know is that we got it through adding an unspecified amount of ammonium chloride into a solution of water. So our initial concentrations of the conjugate base and of hydronium are 0, meaning the equilibrium shift works the same way, where our changes are going to be negative x plus x and plus x respectively. So at equilibrium, our concentrations of the conjugate base and hydronium are x, and our equilibrium concentration of our acid is the unknown concentration minus x. However, since we know what x is, we know that x is equal to 10 to the negative 4.75, which is our indicated pH here. We actually have enough information to back calculate what the original concentration was. So let's begin by writing out our Ka expression and going to our data table to find the actual numeric value. So our Ka is going to be the concentration of our conjugate base times the concentration of H3O+ divided by the concentration of our acid, NH4+, and if we go to our data table, we can find that the Ka value of NH4+ is 5.6 times 10 to the negative 10. So let's get that in writing like so. Next, since we actually know the value of x, we can actually go ahead and substitute it for our 10 to the negative pH value here. So our Ka value, 5.6 times 10 to the negative 10, is equal to X, which is 10 to the negative 4.75 squared, divided by our unknown initial concentration minus our X value, so 10 to the negative 4.75, and then all that we need to do is isolate our unknown in order to solve for it. So that would involve multiplying both sides by the equilibrium concentration of NH4, and then to isolate this, we would need to divide both sides by our Ka value, and then add our X value to both sides in order to isolate the unknown initial. So after I work through the algebra, you should end up with an expression where our unknown initial concentration is equal to our X value, 10 to the negative 4.75 squared, divided by the Ka value, 5.6 times 10 to the negative 10, plus the X value from the equilibrium concentration of NH4, so plus 10 to the negative 4.75. Now, I'm not going to actually put all of this into the calculator yet, because if we take a look at what our question is supposed to solve, we're not actually looking for this initial concentration of NH4. We're looking for the initial mass of NH4Cl that we need in order to get a solution with this pH. So even if you put all of this into a calculator, this is not our final answer, because we're not looking for the moles per liter of NH4. We need to find the mass of ammonium chloride. So to do that, we need to multiply by the volume of the solution that we're dissolving ammonium chloride in, which is 1.5 liters. And then we need to multiply by the molar mass of ammonium chloride. So let's just do a quick reactants and products conversion. So we know that there's going to be 1 NH4Cl for every 1 NH4. This is just to make sure that we're referring to the right compound. And we know that the molar mass of nitrogen is 14.01. Molar mass of hydrogen is 1.01. 1.01 times 4 is 4.04. And the molar mass of chlorine is 35.45. Let's do some quick arithmetic here. And if you check my arithmetic to make sure that it works, you should find that the molar mass of ammonium chloride is 53.50 grams per mole. And if we put all of this into our calculator, you should find that we get the mass of ammonium chloride that we need to dissolve within 1.5 liters of water in order to end up with a final pH of 4.75. Putting all of this into your calculator and rounding to 2 significant digits, you should find that the quantity we calculate comes to approximately 45 grams of NH4Cl. So backtracking to make sure that we know all of the steps to deal with a hydrolysis situation, the first thing to find out is whether the salt, once dissolved in our solution, is going to produce an acidic solution or a basic solution, from which we can come up with our acid or base ionization equilibrium, where solving for the unknown follows basically the same procedure as any other acid or base ionization problem. In the next series of videos, we're going to look at more detailed applications of acid and base equilibria, including pH indicators as well as buffer solutions.